Hi, the next topic is matrix representation. So this is similar to chapter 6. Originally, we defined an equation for each observation, and then we develop expression with matrix representation for all observations combined. So one-way layout is this equation, xij is equal to alpha sub I plus epsilon ij. And we want to use the matrix representation to represent this. So example, so suppose that we have the data with 7 observations. We have 3 groups, the group 1, group 2, group 3. And the variable is length. And we have the values for length. So we have 3 groups. I is equal to 1 to 3. Capital I is equal to capital L is equal to 3 in this case, and the sample size for each group is the 3, 2, 2. Then the matrix representation for this is this. So first group is here. So this first column is the indicator function for first group. Indicator function for first group. So for example, the alpha, so x11 is the 1, 0, 0 times this vector alpha 1, alpha 2, alpha 3. So the product of this is 1. 1 times alpha 1 plus 0 times alpha 2 plus 0 times alpha 3. So this is alpha 1 plus epsilon 1, 1. So this represents, so this becomes the original equation we defined. And the same thing for the second group and the third group. So second group, second indicator, the indicator function for the second group, and the third group indicator function for the third group. So this looks similar to the linear regression if we think this is y, this is x, this is beta, and this is epsilon. So actually, the all estimation of alpha 1, alpha 2, alpha 3 is done by the same LM function. So one-way layout is a kind of different version of linear regression. And a different parameterization. So in the previous example, the matrix representation example, the first column is not intercept. In a linear regression, everything was 1 in the first column, and the second column, x1 to xn. So it's good if the first column for one-way layout is also an intercept, then almost entirely this is the same as linear regression. Actually, the multiple linear regression have multiple columns for x. We have multiple predictors, x1, x2, x3. So, so it's good to have intercept as the first column. So another representation is here. The xij is equal to mu plus alpha I plus epsilon ij. But we have only maybe the L groups. And if we have the mu and we use alpha 1 to alpha L, then we have some redundancy. So so here I use n. So there are n groups for the factor, but we have 1, the redundant I. So in this case, we use only the mu and alpha 2, alpha 3 up to alpha n. So we don't use alpha 1. So otherwise, we have too many parameters, so we cannot identify the parameters. And sometimes, sometimes that we just don't assume alpha 1 is equal to 0, but instead the summation is equal to 0, we assume. So in this model, the xij is equal to mu plus alpha I plus epsilon ij model. matrix representation that becomes this. So first group, second group, and third group. So first one is intercept. And the second group, we have the second one. And third group, we have third one. So I think that this should be mu. So in this case, that you can see that the x11 is equal to 1 times mu. So actually a mu. So alpha 1 does not exist, plus epsilon 11. But second group, the 8.9 is mu plus alpha 2 plus epsilon 21. So in this case, so alpha 1 does not exist. So in this case, basically the mu represents a kind of alpha 1. So the effect for the first level. And alpha 2 represents the difference between the two groups. So here the mu is the mean level for first group. And the meaning of alpha 2 is the mean level of second group minus mean level of first group. So interpretation is different, even though we still use the symbol alpha sub 2. And alpha 3 is also mean level for third group minus mean level for first group. So first group is the baseline. So this is the another representation of the ANOVA. And in chapter 6, we only have the 2 columns for matrix X. It's called the model matrix or design matrix. But in general, we have the P predictors. So in chapter 6, we have just variable X. So we write the X sub 1, X sub 2, X sub n. But now we think about the multiple predictors, such as the weight, height, and the BMI, and so on in the health data. So we have to need an index to represent the first predictor, second predictor, and third predictor. So we say this as x11, x12 to x1n. Then the piece predictor is xp1. The value of the piece predictors are xp1, xp2, and xpn. So multiple linear regression model has this matrix representation. So actually, the chapter 7 is just the special case of this multiple linear regression. And X is called design matrix or model matrix.